Here I'm going through the CAM process for the 135-degree gusset that I've already gone over in class. What I've made here is a little assembly kind of showing you the setup that we would have when manufacturing this part. Again, there are many different ways to machine plate, but some of the hard things that you deal with is holding the flat plate material down while you're machining the part out. One way, and probably the simplest to understand, is to have this sacrificial plate. And in this case, and I showed it to you in class, this is just a half-inch thick piece of polyethylene plastic. It could be different materials. I typically like it to be softer or as soft as the material that I'm machining. Then you can see the stock material, which is the polycarbonate that we're machining the gusset from. And then you can see the actual model of the part. Now, what we would typically do in class is clamp the polycarbonate to the table on top of the sacrificial plate. And so we would have some toe clamps here that we would hold that part down and then machine the gusset from it. Again, there are numerous ways to hold things down. This is kind of the most straightforward way to do it. I wouldn't say it's necessarily the best, but I think it's the easiest way to do it, and it's the easiest way to understand it. So all you need to really do, though, is to understand that it is being held down. And when we actually manufacture it in class, it'll make a little bit more sense as you see the setup. But for the CAM, you don't have to have an entire assembly. You can do the CAM in an assembly like I have here, but I think it's easiest just to have the part like we have it here. And so here's the part, and it's modeled in polycarbonate. And you can see that we have these holes, and then we need to cut it out. And so to make the holes, we can drill them, but I'm going to show a couple of different ways to make the holes in this video. The first thing I want to do is inspect and measure the diameter of the hole. That hole is 0.170. If I actually go to the model, you can see the hole here. And if I double click on it, it's actually 0.1695, but it's rounded up to 0.17 when I showed the measurement. That 1695 is actually the close fit clearance hole for a number 8 screw. And we can see that through bringing up a drill and tap chart. And so if I bring up a drill and tap chart, I'll bring up the one that we've used in class here. You can see that 0.1695 right here is the close fit clearance hole. So it's a clearance hole, close fit for a number 8 screw. And those are the same size of screws that we've used with the VEX material. So this little gusset can be used to align with the square holes in the VEX structure, so that you can attach things at a 135-degree angle with respect to one another. And so that's basically how this part was designed. These holes are a ½ inch apart, just like the holes in the VEX structure. So the first thing we're going to do is go to CAM, and we're going to go to Setup. And the first thing that it does is it gives us the gnomon. It creates some stock material. We need to get things set up properly. I'm actually going to go to the stock first, and I'm going to change the relative size box. I'll keep it there, but let's add material to the side. But we don't want material to the top and the bottom. We want the stock material to be the same thickness as the actual model. So we have that there. So I'm just going to leave it like that. It really doesn't matter exactly how big the stock you have, as long as it's bigger than the part. So I'm going to go here to the stock box point and hit the drop down, and I'm just going to go to model box point. And again, it really doesn't matter where the origin is at. You just need to ensure that you have the Z-axis coming up from the top of the stock. Okay, and so our origin will be on top of the stock material, which is the same as on top of the model. And we have the x-axis, in this case, going to the right, and the y-axis going this way. And that's a great point. You could choose this point as well, but again, don't choose on the bottom. Let's choose on the top here and make sure that the z-axis is indeed pointing upward. All right, so now that we have the origin, once we're at the machine, I haven't shown you how to set the origin or the work coordinate system at the machine, but what we would do is we would set it and define that to be the location of the work coordinate system. And then we would know that the part would be machined. In this case, that would be the lower left corner and the part would be machined above it. And so when we go into the shop and actually make this part, I think it'll make sense more when we actually go and manufacture it. But now that we have the work coordinate system set up, we can hit OK. And now we just need to decide how we're going to machine it. First, let's go to drill. Let's drill the holes. And the tool that we're going to use, let's use the smaller Haas milling machine. So I'm going to go to the Haas TM1. And I have a tool that is a drill bit for that size, 0.1695. It's a very popular hole size. And so I have a tool devoted to it. And so I'm just going to select this tool here and hit select. And then I'm going to go to the next tab, which is geometry, and start clicking on the holes. And now instead of clicking on all of them, I can just go select all holes of the same diameter. Now that I've selected the holes, we need the depth. You can see that the drill bit right now is going to the hole bottom, which is we can keep this at hole bottom, but I do want to go a little bit deeper. And so we're going to drill through the bottom and let's add 20 thousandths just to make sure that we have the hole cleared out with the drill bit. Realize that this drill bit is diving into the sacrificial plate below. So now we have the holes drilled. There is another way to do the holes. Let's say that you did not want to dig into the sacrificial plate. You didn't want to drill into it. You could raise the depth of the drill bit. You could go here and unselect drill through the bottom and then maybe lift it up a little bit, a couple thousandths, maybe we'll go 4 thousandths. But then we have a lot of material left over, and that's going to be hard to clean out later. And so I typically, if I want to get closer to the bottom without touching the sacrificial plate, I'll use a different operation. And one way to do that is to use the bore operation. So I'm just going to show that here under 2D milling. We can go to bore. And instead of a drill bit, we're going to use an end mill. So under the TM1 tools, we need an end mill, a flat end mill that's smaller than 0.1695. And in this tool library, I only have one of those, and that is the tool number 2, which is the 1/8 inch flat end mill. So selecting that, 0.125 is less than 0.1695. I can go select. And the geometry are the holes. I'm going to select those of the same diameter. You can see that we're not drilling in, it's moving in a helical path, cutting the material away. And under depth, instead of hitting the bottom, let's stay up above the bottom by just a few thousandths, maybe 4 thousandths of an inch. And so we're going down and we're staying up above the sacrificial plate. Couple other settings you can play around with. If one thing about that small tool that I worry about with the bore and this helix is it's kind of diving in maybe a little bit too quickly. And so one thing I like to do is define the angle, the ramp angle instead of the pitch, and then you can play around with that. Maybe a 5-degree ramp angle is a good ramp to kind of slowly work its way in and do this helical maneuver to dig out that material. For now, we don't need to worry about anything else on the lead ends. Everything looks good. And so I can just hit OK. And so instead of drilling, I could use this operation here. All right, the next thing that we need to do is now cut around and do a contour to cut the piece out. And so we're going to go to 2D contour, and the tool that we're going to use is the 1/4" flat end mill. That's kind of the standard tool that we use a lot for contouring. And so I'm going to select that. And then the geometry is just the outside. And I selected the top edge. You could select the bottom. Either one will work, but you just need to be aware of how deep it's going when it actually goes through and cuts. And then the depth. For right now, I'm just going to leave the bottom, leave it just as the bottom of the model. So right now, the depth is the selected contours, which is here. That's not going to cut anything. So what I'm going to do on the drop down is go to model bottom, and then I can make sure that I'm cutting to the bottom of the model. I could do stock bottom, again, because the stock is the same thickness as the model. There's some options there. If we wanted to stay off the sacrificial plate, we could be up just a tiny bit, a few thousandths. But for right now, I'm just going to leave it at 0 and hit OK. You can see what's going to happen. We're basically coming in, diving into the material, cutting around, and then kind of leaving with this little exit. Couple of issues here. One, the part's going to fall out due to me cutting completely around. So when I get close, the part might flop around and fall out. So it'd be nice to prevent that from happening. Two, we're cutting kind of deep for the 1/4" end mill. I typically don't like to cut a 1/4" deep with a 1/4" end mill. I try to do about half of that. And then also, I don't like how it's diving into the material as well. If we did a simulate, you can see, if I show the stock, you can see the tool is just diving vertically into the material when it first enters. And that's really not a great way to treat an end mill. You shouldn't be diving vertically into the material, even if it is plastic. So what we're going to do is go and double click on this contour here. First thing in these tabs is we're going to, in the second tab, we're going to add these little tabs to kind of hold the part in place. And you can play around with the numbers. You can see that right now there's only 2 tabs. Their distance, I have them positioned by distance. If we make the distance a little bit smaller, maybe 1.5 inches, you can see I have 4 tabs. They're holding it. Maybe I want them to be a little bit wider. 0.4 might be nice. 0.375 is 3/8, somewhere around there. And then they probably don't need to be quite that thick. We can maybe play around, maybe 25 thousandths. It's kind of difficult to know exactly how thick of a tab you should make, but you realize the tabs that you have, you're going to need to cut off at the end, but it's going to keep the part from flying around when you do cut it out. So that's one thing that we're going to do. And if we hit OK, we can kind of see that we now have these little tabs. If I do a simulate and play this really quickly, you can see that it leaves these tabs here. So that's the first thing we're going to add. Second thing is I said something about the depth. I didn't like cutting so deep in one pass. And so what I do is multiple depths. And then typically on the maximum roughing step down, I try to set that to somewhere around the radius of the end mill. So if the end mill is a 1/4 inch, that's the diameter. So the radius would be 1/8 of an inch, and that is 0.125. So if we choose a right around 0.125, that will be that will break this into 2 different steps as it cuts, and that's a lot easier on the end mill as we're doing essentially we're doing a slot cut because we're cutting through the full width of the material as the end mill is moving through. And so whenever we do a slot cut, I like to cut it down to at least the at least the, oh, what did I say? The radius of the end mill. Next thing I want to do is I don't like diving in to the material. And so what we're going to do is double click here, go to the last tab, and we're going to ramp in. And I just keep the default settings typically. And I wanted to show you what this ramp is. Basically, we angle slowly into the material at this at 2 degrees. And again, you can change that angle, but you can see now in red here, the tool is leading in, and it's not entering the material until it gets over here. And then it slowly enters the material, cuts around, and then for the second depth, it ramps again. And then it slowly goes down and then gets to the bottom. So that looks a lot better. Still a couple things I don't like. One is this exit. So we've ramped in nicely, but when we've exited, we've kind of pushed through all of this material, which is a 1/4 inch thick before leaving. And for plastic, it's really not going to hurt the end mill. It should be able to handle that. But if it were like hard metal, there's a good chance you could break it, especially if it were thicker. And so let's get rid of that curved lead in and curved lead out. We can do that by going here. Actually, I think it's the last tab. And where it says leads and transitions, there's a sweep angle set at 90 degrees with respect to the part. I'm going to change that to 0. I'm going to keep the other settings the same. You can see now when it leads in, it has a 0 degree lead in, meaning that it's kind of leading in parallel to the part and exiting parallel to the part. And so that's going to be a lot safer on the end mill. The final thing that I want to change is the shape of the tabs. Might not be a big deal, but you can see that the shape of the tab is rectangular. The part is going straight up, and then, or the tool's going straight up and then straight down. And so when it goes straight down, it's diving vertically into the material, which again, I'm not a big fan of with the end mill. It's not designed to do that very well. And so what I'm going to do is go double click there, go back to the tabs, and I'm going to change the shape of the tab to like a rectangular shape. Yes, that's less material for the tab, but we can change the thickness or whatever if needed. But now the tool is never vertically diving into material. So if we simulate here, you can see that the tool comes in, it's doing its 2 degree lead in, cutting around, and it's doing the step downs. Now it's going again, diving this ramp, and now it's leaving the tabs. You can kind of see the tabs there. And the goal would be that the part would stay in place before we unclamp it, and then we could break the part out and file and clean up the edges here. Notice we don't need to do the drill and the bore. We can do just one or the other. Okay, and so you can, let's say we want to keep the bore and get rid of the drill, then you would just delete that. Notice the bore takes a lot longer because it's not straight down drilling the part. It's slowly doing that helical maneuver as it digs out the material. So it's a lot slower. And so you do need to be aware of that when machining it. If you don't really care about the sacrificial plate, sticking with the drill bit is definitely the way to go. But if you have a plate like a fixture plate that's made out of metal and you don't want to dig into it, then you should not be drilling. You should use a bore. Okay, so I'm just going to delete the drill here. You don't need them both. And then finally, just to create the G code, you just hit setup. Notice that we have these two selected. We can go post process, select the mill that we're going to use. I have it already pre-selected. It's the Haas pre-NGC from the drop down. And then you need to give it a number. I'm just going to leave it as a default number and then go post. For now, you can just save it to your download folder. What we would do if you were in the shop is you just save it to the USB drive, and then you take your USB drive to the machine, and you take the USB drive to the machine and load the G code. So here is the G code for that part. What you need to do is just give me a small snip of the first page of it would be fine. So if you just snip this out and put it into the Google document, that's all you need to do to show that you've created the G code.